So welcome to the fifth and final lecture of Keith's course. After the lecture, we would have a group photo so that we can have Keith also in the picture for the history of the course, Gravitational Wave School. So please join for the photograph immediately after the lecture.
Okay, thanks, Bala. So in this last lecture, I want to address several distinct topics. First, I want to finish off what we've been discussing so far, which is gravitational wave emission that qualifies as truly continuous. We'll focus on accretion there. And then I want to get into what I call quasi-continuous wave emission, which includes glitches and the aftermath of a newborn neutron star or a post-merger remnant. And those are different enough from a conventional CW signal that they merit some additional specialized discussion. And then later, if there's time, I want to address what I call these lamppost physics topics that are peripherally related to continuous wave emission in that search methods that we use are very similar, and the signals, in fact, could in principle be confused with those of a CW signal from an ordinary neutron star. Okay, but let me begin today by addressing this last topic I wanted to consider in conventional continuous wave emission, and that's the topic of accretion. Now, as I've alluded to before, for accretion in a binary system with a companion accreting onto a neutron star, it's not crazy to expect that there would be some non-axisymmetry created by this matter falling onto the star, particularly if the neutron star has a strong magnetic field that tends to channel the plasma that's falling on it into regions near the magnetic poles. So you don't necessarily expect isotropic or even axisymmetric mass deposition in that process. At the same time, although this provides a natural mechanism for building up a non-axisymmetry, there's also a competing tendency, which is the annealing we've discussed earlier of a neutron star. It has a very strong tendency to make itself as axisymmetric as it possibly can. And also the matter that falls on the star tends to diffuse and spread out deep inside the crust and laterally. So those tend to work against this notion of building up a non-axisymmetry. One thing to keep in mind is that as the mass sinks into the star, it can also at the same time, because it's typically hotter than the material it's falling onto, it can create hot spots beneath the surface that themselves lead to mass density fluctuations, which look like a mass quadrupole. So there are a lot of competing effects. Different theorists have different opinions as to how likely it is that you could build up a significant mountain, so to speak, or even a subsurface mountain through this process. But at least it has some potential. Now that said, there's actually some intriguing evidence, empirical evidence, that something like this might be going on in certain systems. There's intriguing evidence from low mass X-ray binary systems, LMXBs, of what's known as a rotational speed limit. And also from the millisecond pulsars that we've already discussed. There is evidence of a speed limit. Earlier in the week, we looked at some estimates of the Kepler speed limit from mass shedding. And you found frequencies, rotational frequencies above 1,000 hertz. Yet, we don't see any millisecond pulsars or any low mass X-ray binary stars that have frequencies close to that Kepler limit, which suggests that something's going on. Why don't these stars just spin up arbitrarily fast until they hit that mass shedding limit? Okay. So the model we have in mind is that we have a neutron star in orbit with a lighter companion. And that companion is overflowing its Roche lobe, raining matter down onto the neutron star. And in this model, we think that the low mass X-ray binary, in fact, is a pretty decent candidate precursor to the millisecond pulsars that we've already looked at. This is a very good explanation of how they came to be, as I've mentioned before. In fact, this idea is strongly supported, also empirically, by a handful of special stars that are known as transitional MSPs. And these are systems where you see alternation between radio pulsations of an ordinary star. In a binary system, you see alternation of that pulsation mechanism with accretion. For example, I believe this is the first one that was discovered, J1023 plus 0038 is a star that sometimes pulsates and sometimes doesn't, but when it doesn't, it tends to be showing evidence of accretion from its companion. So this is an alternation of pulsations and accretion. And presumably that's because these are systems that are going through a transition that will eventually lead to a complete decoupling of the companion, and it would just become a millisecond pulsar. The fastest known millisecond pulsar is about 716 hertz. That is the extreme outlier. Most of them are well below that, of course. Okay. The fastest known LMXB spin is about 540 hertz. And the fastest known nuclear-powered pulsar, I'll put pulsar in quotation marks because it's not really a pulsar, it's basically an accreting system where you have a thermonuclear burst on the surface, and so for a brief period of time, as that hot spot goes around and around the star, you see a burst oscillation, and from that you infer the frequency of the star. And that one, I believe the fastest one is 619 hertz. So they're all in the same ballpark. Okay. And the natural question is, what prevents them from going even faster? What prevents accretion from reaching the shedding limit? Now, one possibility is something very mundane, ordinary. So it may just be some ordinary interactions in this very unordinary system, but very ordinary interactions between the neutron star magnetosphere, and typically you would expect it to have at least some decent magnetic field associated with it, and this plasma accretion disk surrounding it. You know, this is, of course, a process that famously is not well understood. So there are lots of different models out there for how this works, and some of those models would predict breaking, that the accretion disk itself tends to keep the star from spinning up too fast because of the coupling between the magnetic field locked to the star and a magnetic field that also interacts with that disk. But another possibility, the one that we find intriguing in the continuous wave community, is that it may be due to an entirely different process. It may be entirely due to gravitational wave breaking. With ellipticities, they don't have to be that high. An ellipticity of 10 to the minus 7, which, as we've seen, is very much allowed, we think, by equations of state, could explain this. So let me show you a graph, basically a histogram, of some of these measured frequencies, along with an analysis by a group that thinks that this really is evidence of gravitational wave breaking. Oops, that's not right. Here it is. Okay, so here we have a histogram, a distribution of the spin frequencies of some accreting systems. In some cases, these are low-mass X-ray binaries. In some cases, they are nuclear-powered stars with these burst oscillations. And these curves shown here are basically just Bayesian models of what's going on, and they claim there's pretty strong evidence here of a bimodal distribution. And their argument is that these guys at the highest frequencies are the ones that are being directly limited by gravitational wave breaking of the spin. They can't get any faster than that. I'll come back more quantitatively to that idea in a moment. And then these are stars that are not in that mode. They have spun down over some period of time, and they are the precursors to millisecond pulsars. In fact, the mean of this distribution is very similar to the mean of millisecond pulsars. And so in this model, you have an accreting system that spins the stars up to these very high frequencies, but for the most part, by the time we see them as radio pulsars later, they have spun down. But during the accretion process, they're going about as fast as they can. All right, so that's the basic idea. That's some of the empirical evidence for it. I should also mention that this set of stars is hot, hotter than these others. In fact, I think if I remember correctly, these stars all have measured temperatures where these just have upper limits. And one possible explanation for why these stars are hotter is that they're being heated up by R-mode processes. I'll come back to that later, that idea later on, as to how R-modes might play a role in a system like this, because you might be surprised by that statement. So we could be seeing both a torque breaking and heating due to R-mode generation in these stars. Okay, so let's see how this works. Why does this make any sense? So we're imagining a torque balance scenario that looks like the following. I'm just going to very crudely, briefly summarize the notion. But in this scenario, we reach some sort of steady state equilibrium in which the growth of the star's mass due to accretion, dm dt, is proportional to the gain in its angular momentum, because the matter falling on the edge of the star tends to spin it up. At the same time, we are emitting gravitational radiation as a result of this faster speed up. And in the torque balance scenario, those two balance each other. That's why you end up with some speed limit where you have this balance between gravitational wave angular momentum loss and the gain in angular momentum from accretion. And so there's a proportionality between the gravitational wave loss in angular momentum, because it's the same as what we're gaining from the accretion, and this mass accretion rate. And note that the loss in angular momentum due to gravitational waves is proportional to the square of the gravitational wave strain as seen by some observer at an arbitrary distance. And at the same time, we can also infer a relationship between the mass accretion rate and the amount of radiation energy in X-rays. That's how we measure accretion, is by the X-ray intensity. And so there's a natural way to relate these two. There's an idea that I think was first propounded by Robert Wagner back in 1983. And if you put these ideas together, you have an inferred torque balance strain that looks like something in the ballpark of 3 times 10 to the minus 27 times a radius, I'll call the accretion radius, over 10 kilometers to the 3/4 power times 1 over the mass of the star in units of solar masses. This is actually a slightly simplified version of the formula. There's a more sophisticated version of it. I won't give it to you. And in addition, you need to put in the frequency. We have 1 kilohertz over the rotation rate, not the gravitational wave rate, but the rotation rate, the 1/2 power. And we have a flux rate in X-rays, and I'll put in a benchmark of 10 to the minus 8 ergs per square centimeter per second. And so this flux in X-rays is what is observed by the observer wherever the observer is. You'll notice that that formula does not have a distance in it. And that's actually helpful in many ways, that it does not have a distance in it. So that's the observed X-ray flux at the Earth due to the accretion. And so if I plug in some numbers, I have, I assume M is equal to 1.4 solar masses, and I take the accretion radius to be the same as the radius of the star, which I'll take in this instance to be 10 kilometers. I assume that those two radii are the same. I'll come back to that in just a second. Then I find that H torque balance is of order 5 times 10 to the minus 27 times 600 hertz over, and now I'm going to use the gravitational wave frequency as a benchmark, because that's what I'm going to actually look for, the 1/2 power, times this flux over the same benchmark of 10 to the minus 8 ergs per square centimeter per second. Let me note that if the accretion radius that matters is not the radius of the star, but instead is the alpha n radius, where you have magnetospheric torque increase, which would be much further out. If that's the case, then you boost these estimates significantly. The strain in that case increases by about 2.4. We normally try to be conservative and assume that these two radii are the same. But if you do distinguish between them, there's a slightly more refined model for this process that one uses. Okay, now let me come back to this point that there's no distance in that relation, unlike all the other relations we've seen for gravitational wave strain. The reason for that is that both h squared and the X-ray flux fall off for an observer as 1 over the distance squared. So because of that, the estimate for the torque balance strain is actually independent of the distance to the source. And that simplifies trying to assess which sources are more promising. We don't even need to know what the distance is to the source, unlike the case for most of the other searches we carry out, where we have to make a decision, is this star worth pursuing with extra computational resources? Here, it's a very easy decision, because the most promising source in this argument is the one that is X-ray brightest. And there's one clear winner in that contest. Given that criterion, Scorpius X1 is the guy we need to focus on. It's about 2.8 kiloparsecs, but as I said, this argument doesn't depend on how close it is. It's good that it's not too far away, in some respects. Its X-ray flux is 3.9, on average, 3.9 times 10 to the minus 7 ergs per square centimeter per second, which is well above our benchmark. And if you work out the numbers, what you find for SCO X1 in this torque balance scenario is you'd expect a value of about 3.4 times 10 to the minus 26 for the strain if you had a signal at 600 hertz in gravitational wave frequency, raised to the 1/2 power. Let me comment on that 1 over the square root of frequency dependence. That's unfortunate as far as the search is concerned, because it makes it harder to look for this thing at high frequencies. 600 hertz gravitational wave frequency is only 300 hertz spin frequency. If the system really is going through a torque balance equilibrium scenario, then it's probably at a higher frequency than that, maybe by a factor of 2. So you're down even more as a result of that. So that's one problem with these higher frequencies. Another issue is that detector noise is worse at higher frequencies, significantly worse. If you go up to say, let's say as high as 1200 hertz, assuming it's 600 hertz times 2, then your noise has gotten significantly higher. And then another issue that's even worse than that is that in these searches, we're using semi-coherent techniques that Alicia's talked about. And the problem with this system at high frequencies is that you have an enormous frequency modulation due to the orbital system itself. Its orbital period is only about 19 hours, but it goes through a comparable modulation of its frequency to that due to the Earth's entire annual frequency modulation. It's about 10 to the minus 4. And so that means that you have a frequency that's changing on you radically fast. And that effect gets worse and worse at higher frequencies. And that means you have to use, at least in our current techniques, you have to use shorter and shorter coherence times. And that, as Alicia has described, I think, hurts your sensitivity significantly. So it's hard to go after SCO X1 at high frequencies, but that may be the very place where we need to go. So searches are now probing this limit and beating it at low frequencies. That was a nice milestone we reached in the '03 run, was to actually get down and distinctly beat the torque balance limit at low frequencies. But we have a long way to go before we can beat it at the higher frequencies where the source signal is more likely to be, at least if the torque balance scenario makes sense at all. Now, I mentioned earlier that R modes could play a role in this process, and that may surprise you because I talked earlier about R modes in the context of newborn neutron stars and how that would tend to spin a star down to something like 100 hertz. But there's a different scenario where they could play a role in binary systems like this. Let's return to our qualitative diagram of the R mode instability window. Let me draw that diagram again. So my horizontal scale is basically logarithm of the temperature, and my vertical scale is a linear scale in the rotational angular velocity. And we have this window of instability, like something like that, where we said that over here, at very high frequencies, or excuse me, very high temperatures, we have bulk viscosity that tends to suppress the R mode growth. And down here, we have shear viscosity, which also tends to limit it. And we noted before that if a newborn star comes in from the right, it goes into here, it zips down here, and then it moves horizontally, slowly over time, like so. It just cools off as the temperature gets lower and lower. But there is a possibility that in an accreting system, that this accretion, which can take place over millions of years, that you end up in a place like this, and it starts growing, and the system increases its angular velocity, and if it keeps going and going, at some point it gets back into the instability window. If it gets to the instability window, then it can excite these R modes. So here we have cooling, ordinary cooling. And then in this region, we have spin up from accretion. We go into this window, and in this window, R modes get excited. And R modes, because of the very viscosity we talked about earlier, that eventually limits their amplitude, that creates heating. And so the star starts heating up again, gets itself more into the instability window. There's more growth of the R mode. And eventually the R mode gets powerful enough that it sends the star back down this path due to spin down from the R mode itself. And then it starts cooling off again. And so if you have this energy source of accretion, you can drive a cycle. So this leads to a cyclic pattern that, at first glance, that looks promising. It means that you have if you have an accreting system like this, it could go through these cycles over and over again, and you want to catch it when it's in, ideally, this part of the diagram where the R modes are excited and maybe spinning down. And this is actually quite a significant spin down here. The problem is that if you look at the time scales for the different cycles, this takes a lot longer. We're talking millions of years to speed up the accretion, whereas this can happen over a relatively short period of time, years, tens of years. And so the chances that when you're looking at a particular system today, 2024, the chance that it's in that part of the cycle that is detectable is pretty small for any given system. But nonetheless, it's an intriguing possibility. Yeah. long-term average, yes, but short-term, no. So in the short term, this thing is, if you get into this mode, then you're driving it down very fast. So you're definitely not maintaining a balance. But you can say on a long-term basis, yeah, there's some kind of an average that works out. But this is in some sense independent of the torque balance argument. This is simply saying that if you're trying to explain why it's plausible that you would have this kind of gravitational wave emission in a low-mass X-ray binary system, this is actually a nice way to account for that kind of emission, because it doesn't require as much of a mass asymmetry. I mentioned earlier that theorists disagree about how much of accretion, how much asymmetry you can build up from accretion. This doesn't have that problem, at least not to the same degree. Here the issue is, does the dissipation of the R mode make it less favorable? Now in practice, this simplified model I've shown you here actually may be too simplified. It could be that as soon as you get into this instability window, you go through a tiny little jog and then you kind of stair-step your way down and then do the cycle. But yeah, this is just giving you motivation for why you might expect to get a significant amount of radiation in this process. Okay, so that's all I wanted to say about accretion, and all I wanted to say for the moment on conventional continuous wave emission patterns. Let me now turn to what I alluded to earlier, which are quasi-continuous processes, ones that are similar enough to continuous wave processes that many of the same techniques apply, techniques for searching apply, but with some modifications. In some cases, very significant modifications, but it's the same basic approach. So there are two quasi-continuous wave neutron star emission processes I want to discuss. One is the category of glitches, and the other is a category of post-merger remnants from a binary neutron star merger. And the same ideas also could apply to a newborn neutron star. Okay. Let me talk first about the glitches. So we observe that many young pulsars display what I've referred to many times now as glitches. Recall that graph I showed you yesterday of J0537 minus 6910, which is going through glitches roughly every 100 days. So it's a relatively young source that is spinning down, and it's clearly, in some sense, changing its configuration pretty frequently. So that's characterized by a sudden change in F and F dot. Here I'm referring to the rotational frequency, not the gravitational wave frequency, because that's what's actually observed in these observations. So there are possible causes that have been posited for these glitches. One that naturally jumps to mind, I've alluded to previously, is you could have crustal cracking from spin down and or cooling. That's a very natural way to explain little shifts in the frequency of the star as it cools down and as it spins down and changes its shape slightly as it gets less oblate. Another possibility is a magnetic flare. And we have some pretty dramatic examples of magnetic flares even in our own galaxy, where there's an enormous amount of energy release from the release of magnetic field energy within the crust of the star. Yeah. And then there's another contributor, which I'm actually going to focus on, because it's the one that seems most likely to explain at least a large category of the glitches that we observe. That's a resinking of the core and crust rotation. This doesn't necessarily involve any cracking of the crust, just a resinking of those rotation frequencies, because in general, you can build up differential rotation between the inside, the internal part of the star, the core, and the crust itself. So the crust, if you have ordinary magnetic dipole emission, the crust is going to spin down, but if it's not firmly locked to the core may not spin down at the same rate. So let me address that. Let me also point out that this process could produce, in contrast to the nominally continuous wave scenario, it could produce a temporary enhanced asymmetry. Before annealing. Particularly in the scenario of crustal cracking. We expect, as I've said before, annealing to take place. And so this might actually subside in some period of time that's actually comparable to the observing time. And so you would not see a constant amplitude signal, you'd see a signal whose amplitude would slowly decrease with time. And that's different from what we normally assume in continuous wave searches. But for some period of time, we would have radiation at gravitational wave frequency at twice the rotational frequency. And these glitches are not that big, as you've seen. So you don't have to change your search strategy all that much. It's just that for some period of time, you expect a stronger amplitude. And a star that you might not normally pay that much of attention to because you think of its a nominal spin down limit is just too low to be accessible, it might become temporarily accessible in the aftermath of a glitch like this. All right, so let me get back to this one specific scenario I listed last there. And I'll treat it in what's known as the two-fluid model. This is following the analysis of Oraiges et al., relatively recent paper. So the idea is that we have a crust and a normal part of the neutron fluid, so not the superfluid, but the normal part of the neutron fluid in that core, that are co-rotating at the omega that we would observe for that star, what we see electromagnetically. And that omega decreases as we have magnetic and possibly gravitational wave radiation emitted. Because again, we would expect, at least naively, that the gravitational wave emitted would be due to the crust. But the superfluid component may not be co-rotating. It it could have its own omega, I'll call omega S, that is somewhat greater than omega, at least until there is a resyncing of these rotation rates. Now, we expect that to happen eventually. We don't expect the differential rotation to just build up arbitrarily large. There's a natural tendency for them to resync. And again, this is something in the category of for which the details are not well understood, but at least qualitatively, one model that one can use is that the pinning and the unpinning of the superfluid vortices that provide its angular momentum to the crust is likely relevant. That would be a natural way to limit how much differential rotation can build up as the crust spins down and the superfluid doesn't initially. Eventually, we do expect them to sync up. But that can be a very sudden process. So one can make sort of back of the envelope estimates of how important that is, how much energy is involved in that. So just to set the scale, one can set an upper limit on the total energy that is released, and one can, pretend, at least for the moment, that all of that energy is available to gravitational wave emission. That's not likely to be the case in reality, but at least it gives you an upper limit. And so what you could say is that the amount of energy that's available is 1/2 of the moment of inertia of the superfluid times the difference in its rotation rate, angular velocity squared, minus that of the somewhat slower rotation rate of the crust. So if you resync it, you're giving up that rotational energy, and maybe, if you're lucky, that goes into gravitational radiation. So if you work out simple algebra, you'd say, well, that's approximately 4 pi squared superfluid moment of inertia times the rotational frequency, cycle frequency, times this lag frequency between the two rotation rates. Now, we don't know what they are because we don't know how fast the internal superfluid is rotating, but whatever it is, we can characterize it in that way. Now, as I said, we don't expect it to get very large. We expect this delta F lag between the two components to be much less than the rotational speed itself. And let me just spell out that this ISF is the superfluid inertia moment, which in general is going to be generally quite a bit smaller than that of the star itself. It's only one component of the core. Now, given this rough upper limit on how much energy is available to gravitational waves, we could make this optimistic assumption that we can then equate that to the integrated emitted gravitational wave energy. So we would say that that gravitational wave energy can be found from the following integral: 2 pi squared c cubed over 5g times f GW squared d squared, the distance to the source. So this is a case where the distance does matter, times the integral from whenever the glitch started to our end observation time of whatever the amplitude h0 squared is over time times dt. And h0 is not going to be a constant. We expect h0 to decline with time. And so it's conventional in this kind of analysis to now define an RMS amplitude averaged over that observation time when you're trying to detect this potentially enhanced gravitational strain amplitude. So one can define root mean squared amplitude square root, I should say, H naught average defined to be 1 over the distance times, actually, let me step back a moment. Let me say that H naught average squared is defined to be 1 over T times whatever H naught squared of T dt is. And then with that definition, I can say that H naught average is less than or equal to 1 over d times the square root of 5g over 2c cubed, the moment of inertia, times delta f of the glitch. So now this is the observed glitch over t over f rotational. Now I'm using the moment of inertia of the star. So I'm basically saying that all of that angular momentum has been transferred into the crust. Because what will happen is that when you get that resinking, the faster spinning inner core is going to speed up the crust momentarily. But then you'll have a continued spin down from there. So let me spell that out explicitly. I'm basically making the approximation that I times delta FGL, which is the observed glitch of the crust, is approximately I of the superfluid times a delta F lag, which will in general be larger than what we observe. Okay, now as a benchmark, just for understanding what is detectable, one can assume, and this is definitely an artificial assumption, but just for the sake of making ballpark estimates, one can assume artificially that the signal has a constant amplitude for an observing time that I'll call tau, and then you get a crisper definition of what the amplitude is. But then you have to make an assumption about what the right time scale is. So H naught, under this assumption that it just turns on for a period tau and then turns off again, this rectangular shape, then is less than or equal to 1 over d 5g over 2c cubed I over tau delta f GW over, oh, sorry, not GL, GW GL over f rotation. Okay. And so then one can convert that to an upper limit. And again, we're just talking about upper limits, making a very optimistic scenario assumption. But you can derive an upper limit on the generated ellipticity associated with that glitch, just based on saying that that ellipticity is what gives you this gravitational wave energy, which we are ascribing to being due entirely to the change in the rotational energy of the superfluid. And what you find is that epsilon tau, for a given assumed observing time corresponding to the actual turn-on time, is less than or equal to 1 over 16 pi squared times square root of 5 over 2 c to the fifth over g, 1 over this moment of inertia, the time scale tau, and the magnitude of this glitch, delta f gl, over the rotation to the fifth power. All of that is inside of a square root. So notice that in this formula, we have a sensitivity to epsilon that improves as 1 over f rotational to the 5/2 power, and as 1 over the square root of the time scale over which the glitch is active and for which we assume we can search in some optimum way. Let me show you a table from this paper I mentioned earlier that is basically a table that is a compilation of information about a large variety of glitches. So it's a table of historical glitches from a pretty decent number of stars, including Crab and Bala, which I've marked up there. What it shows you is the, well, first of all, the gravitational wave frequency you would expect, being twice the rotation rate, and then what you would get for the maximum strain for a variety of different glitches that have been observed over the years. And this column here tells you what fraction of those glitches would have been in principle detectable in the 04 run. So should that particular glitch happen again, would we have any chance of seeing it with 04 sensitivity? And so you can see that in most cases we don't. You know, altogether, only 36 out of 726 qualify, but it's a non-zero number. So at least in principle, some of these historical glitches, had they occurred during 04, would have been detectable. If you go to 05 with better detector sensitivity, the fraction grows by roughly a factor of 2. So there's some hope that if a glitch like this happened again, that we would be able to catch it. But again, I have to remind you, this is a very optimistic scenario I've assumed here, where all of that energy that we think was released by the in the resyncing process is indeed available in the form of gravitational wave radiation. And there's good reason to think that there are other energy factors, energy dissipation mechanisms that also apply. I'll just note that if you have a long persistence of a signal like this, that's good for accumulating signal to noise ratio when you're doing a search for something like this, because that means you have a very narrow band signal, and so you just have less noise that you have to fight in that integration. But as you've probably learned from Alicia's lectures, there are some downsides to those long persistences. That long persistence is bad with respect to the trials factor associated with the search. And that's especially true if there is a significant uncertainty. In the timing models. Because sometimes these glitches aren't detected until a significant amount of time after they happen. Days or even weeks after they happen. And so now you're trying to infer back in time when exactly did that glitch take place, what was the starting frequency, what was the ending frequency after the glitch, and that's information that you need in order to do a very sensitive search. I'll just say that the prospects for this kind of detection are quite a bit more promising for 3G detectors than they are for current detectors. We'll have to be pretty lucky, I think, to catch a glitch like this with the current ground-based detectors. Okay, let me switch gears again and talk about this I'm sorry, the question? Sorry, question? Okay. Let me switch gears and talk about this other type of quasi-continuous gravitational radiation, namely what you might expect from the birth of a post-merger remnant in the aftermath of a binary neutron star merger. Okay, so we have two merging neutron stars. And we expect nominally, this is what we normally assume is happening. Nominally, we expect a final black hole with a mass in the ballpark of 3 solar masses, maybe a little less than that, maybe a little bit more than that, depending on what the initial stellar masses were. But it's also possible, although this is almost certainly what's going to happen eventually in these stars, in these systems, but it's possible that that collapse to the black hole may be delayed. By the fact that the star initially has a very fast rotation. So we may, in fact, have a supramassive star if the right equation of state applies. And it may be something that is co-rotating, more or less as a rigid body, or, it may also be differentially rotating, which would allow it to evade the Kepler limit more easily. Okay. The plausibility of this, of course, depends on what your assumed equation of state is. Now, there is some observational support for the idea that these remnants do not immediately collapse into a black hole. Now again, those of us in the continuous waves community tend to be optimists, and we tend to look through a rose-colored lens at any kind of evidence that gives us hope that there might actually be a signal. But let me spell it out for you. So we have some observational support from sustained X-ray plateaus. I'll put plateau in quotation marks, as you'll see why in a second. These plateaus sometimes are seen in the aftermath of short gamma ray burst. We think that most, maybe all, short gamma ray bursts are the result of the merger of two neutron stars, or in some cases possibly a neutron star and a black hole. We have a much larger sample of short GRBs to look at than we do for binary neutron star mergers that we've detected gravitationally. Let me show you one of these graphs that is meant at least to suggest the possibility that there is a, quote, plateau in the light curve, X-ray light curve, following a short gamma ray burst. So here are two examples showing that those red squares are basically a model. Basically, the model is saying that there is evidence here in this little tiny hump you see here, and this little more pronounced hump, that there's a contribution to the X-rays due to an underlying engine, so to speak, from a residual post-remnant merger. That it's not just a black hole that happened after the short gamma ray burst. In fact, there was something still remaining in place. And I'll show you some other examples in a moment from long GRBs. But based on evidence of that level, which again, if you're very optimistic, you would take hope from that. The idea is that this supermassive star may well persist for a significant amount of time. Nothing like the time scale that we use in ordinary continuous wave searches of a year or 2 years or so on. It's a much shorter time scale, but nonetheless, the signal does have the properties of being reasonably continuous. It may persist for order seconds, maybe order minutes, maybe order hours. And there are some cases where there's evidence of multi-hour sustained emission of this type. Okay. So the initial spin, giving us this gravitational wave emission, we hope, is also likely accompanied by a high magnetic field. And so one would expect to have a millisecond magnetar. And you may, in addition, have a quite substantial gravitational wave asymmetry, ellipticity. So we could have an extreme rapid spin down until collapse. And this is a spin down that would be orders of magnitude higher in that first derivative magnitude than we are normally accustomed to in continuous wave searches. Something that doesn't take decades to drop a tenth of a hertz, but takes minutes to drop tens of hertz. It's a very different extreme system. So there is some evidence that at least some remnants from these short GRBs, as I said, we have a fairly large sample of short GRBs to look at over the last several decades. There's some evidence that they have some spin down contribution from gravitational wave emission. And actually, I should say, instead of short, I should say short and long. There are actually some long GRBs due to massive star collapse that show this kind of evidence. And that evidence is an inferred breaking index near to 5. Our magic number if we have quadrupole mass emission. Now these models, this evidence I'm quoting, is of course extremely model dependent, but the model that's assumed is that you have a spin down luminosity of the form luminosity due to spin down is equal to some initial value times a factor of 1 plus time t over tau raised to the power of 1 plus n over 1 minus n. And if n is greater than 1, then that's, it's basically inverse power, really. And so one can do fits to light curves based on that modeling. And Bayesian fits to the light curves. So these are X-ray light curves. Then yield, under this model, both an estimated spin down time that we characterize by that parameter tau, and this inferred breaking index. And as I've mentioned, it's not just short GRBs that are necessarily of interest. Long GRBs may also lead to supermassive stars that could be doing gravitational wave spin down. So in fact, the same kind of analysis has been applied to long GRBs. So these are due to the collapse of a very massive star. And I would say there, the evidence for this kind of a spin down is actually stronger. Let me show you some light curves from these long GRBs from this same paper I used a moment ago as a reference. So these are short GRBs, and then here's a sample of long GRBs. And so here, this model shown in the red curve, it doesn't look as tenuous as it did in those short GRBs. And in particular, it looks great for this guy, GRB 06 1121. It's a long GRB. It's a long way away. It's not that we could actually detect this thing. It's much further away than what is feasible for us. But nonetheless, you look at that model and say, okay, that doesn't fit so badly. And let's see, I think I have a table for them. Yeah, so let me show you a table based on this compilation of these different short and long gamma ray bursts. And these show you the Bayesian fitted breaking indices for these different GRBs. And the one I just pointed to is this one, 06 1121, that works beautifully as a model. And look at that breaking index. Relatively small error, and it's very close to 5. So, again, if you're an optimist, which you must be if you're in the continuous wave community, that looks pretty promising. That there is this kind of emission happening. This particular source would not have been detectable because it's too far away, but it does suggest that this model actually has some potential promise to it. So let me address more quantitatively this issue of the distance to the source, because that is a very important constraint. Oops, so let me go back. Didn't mean to show that quite yet. I'll just stop sharing. Come back to that. Okay. All right, so one comment I can make about this is that unlike with the glitches we discussed a few moments ago, where the available energy was pretty limited, here we have a very different regime. Here, there is enormous energy available for this process. Because after all, we're talking about bringing together two neutron stars, high speeds, and combining them together. But the problem is, as you might have guessed, the sources are very far away. So unlike our conventional continuous wave targets, which are neutron stars in our galaxy, meaning they're kiloparsec, maybe 10 kiloparsecs away, we're dealing with a whole different order of magnitude in terms of distance. And so we need an enormous amount of energy to go into gravitational wave emission to begin with, to have any prayer of being able to see this with our detectors. So as a reminder, the closest BNS detection to date, which was the first one, was at 40 megaparsecs, not kiloparsecs, but megaparsecs. So that's a challenge. And so you need an extreme ellipticity from the star, the supermassive star, to have any chance of seeing it. Or if you like, an extreme R mode amplitude. If you want to have any chance of seeing this thing. Okay. Yeah, but on the other hand, we do, after all, have two merging neutron stars that are at the point of merger distinct from each other. So there is a certain amount of potential there. You know, at the point of merger, when these two stars first come into contact, you have this kind of a situation, and your ellipticity is of order 1. Not 10 to the minus 6, not 10 to the minus 9, but of order 1 initially. Now, of course, it's not going to stay that high, but you know, if it retains 10% or even 1% ellipticity, it becomes interesting. So now if you want to try to calculate the detectability of this kind of a process, where you have a supermassive, hypermassive neutron star in the aftermath of a merger, you have to take into account the bandwidths that you need to search over. And unfortunately, for a process like this, if you don't have any independent evidence of what the initial spin is or how it travels with time, how it evolves with time, then you have to search over an enormous parameter space. In fact, it becomes intractable to try and do this using a match filter over, say, even hours. It's because the frequency derivatives you would expect are so large that the dimension of parameter space you have to search over becomes too difficult. It is mitigated to some degree by the fact that we know the start time if we detected the merger gravitationally. That helps. And of course, we know the location in the sky, particularly if an electromagnetic counterpart has been found. We know it very precisely. So that does reduce to some degree the computational load, but nonetheless, the fact that you have so many frequency derivatives to worry about makes this a very challenging search to do coherently. It's a very active area right now to come up with alternative ways to go after a source like this using techniques involving semi-coherence, Viterbi methods, machine learning, and other ideas are being explored. But it's still a very active area of research. Let me comment that for this detection at 40 megahertz, the worst search is carried out for 1708-17. And the problem that we ran into was that we were 1 to 2 orders of magnitude too weak to even have a chance of detection, even for the most optimistic scenario. And that was true whether we were looking for a very short-lived supermassive star using what are called long-lived transient techniques, or we're using transient CW search techniques. So you're coming at it from both directions in terms of the time scale. Still, no matter which method you used, you needed, for the emission itself, to involve several solar masses worth of energy to be radiated for the signal to be detected here at the Earth 40 megaparsecs away. And of course, that was not possible. So it was, we never had any prayer of seeing this signal. We basically use this as practice so that if we ever get a closer signal than that with a more sensitive set of detectors, maybe we could actually get lucky and see something like this. And I guess I could comment that the same techniques that you would use to look for a post-merger remnant are also applicable in principle to a newborn neutron star in our own galaxy. But of course, it needs to happen, and those things don't happen very often in our galaxy. So if we were extraordinarily lucky enough that we had a supernova go off, core collapse supernova go off in our galaxy during 04 or 05, we'd be in heaven looking for that guy. We might actually have a chance at it. And the same techniques that we would develop for a post-merger remnant would apply there also. And we'd have more promise, I think. Okay, so let me finish with just a very qualitative set of statements about what I called lamppost physics. And let me show you that cartoon that I didn't mean to show you quite as soon as I did. But it's an old joke. It has different flavors to it. But the idea is that someone loses his wallet or his keys, and someone else asks him, well, did you lose them here under this lamppost? And the answer may or may not be yes, but even if it's no, he's still looking there because that's where the light is. Okay, so that resonates with me in terms of some of the searches that are sometimes carried out, not just in gravitational wave physics, but I would say more generally, say in the particle physics community. Same sort of ideas apply. So the reason I mention them here is not because these involve gravitational wave emission from a neutron star, but because the signatures that you would see in your detectors would look a little bit, in some cases a lot like a conventional continuous wave signal from a neutron star in our own galaxy. So but there are similarities and there are also some differences. I'll talk a little bit about those in remaining time. In some cases, the similarities are great enough that you can literally take the results of a search, an unsuccessful negative search for continuous wave emission from a neutron star, and simply reinterpret those limits in terms of some other parameter space related to this particular physics scenario. In other cases, you need to, to get better sensitivity, you need to tweak your search method to do a little bit better. And in some cases, you really need to do more than tweaking your search method. You really need to revamp how you approach it. But nonetheless, it still has many of the same features of a continuous wave signal. So I would say all of these categories I'm going to list are good examples of lamppost physics. And the reason I say that is that in each case, you might potentially see a signal like this in the current gravitational wave detectors, but the part of parameter space that you're looking at is a tiny fraction of what applies to that physical scenario. So you have to have a just so situation where a particular mass, for example, happens to line up very nicely with our particular detection band here on the Earth, but that mass could be orders of magnitude larger or orders of magnitude smaller. Okay. Now, to be fair, in some of the cases, there are other lamps, so to speak, in other bands corresponding to other mass parameters, for example, that allow other searches to take place. We're not the only way to go. But nonetheless, we'd have to be extraordinarily lucky for our gravitational wave detectors to be the first ones to see the source. That said, I'll just remind you that when Anthony Hewish and Jocelyn Bell built that radio array to detect quasars, they had no idea they were going to discover pulsars. And so, you know, if we're lucky, these things built for gravitational wave detection will also detect something completely unexpected. So let me just list these lamppost topics, one of which you actually learned quite a bit about last week, boson clouds surrounding black holes. So that's a case where you get a signal that looks like a continuous gravitational wave signal. It really is a continuous wave gravitational wave signal. It doesn't have quite the same properties as in its evolution with time as a signal from a neutron star, but nonetheless, it's a pretty good proxy for a continuous wave system. Another possibility would be solar system objects, which would include dark matter, whatever your favorite dark matter model is. And that could include, in fact, primordial black holes, relatively light such holes created during the Big Bang, not through ordinary stellar evolution. But they could be here in our own solar system. And they could, in principle, emit continuous radiation. And then there's another possibility that's even further afield. One could, if really lucky, detect ultralight dark matter through its interaction with gravitational wave detectors. So I'm just about out of time, so there's not much I can say about each of these, but let me just make a few general comments. So for the boson clouds, as I said, that really is a continuous gravitational wave signal. The main difference is that if you're relying on the annihilation process to give you, as opposed to the transition process, I mean, you learned a lot about these last week, so I'm not going to go through a basic review of that. But you could have emission from a transition from different hydrogen-like states, or you could have annihilation of the bosons into continuous graviton emission. In that latter case, as the star spins down, it loses energy, it loses mass, and the binding energy is actually reduced in its magnitude. As a result, in that particular scenario, the frequency actually goes up with time instead of down. Of course, in our ordinary searches, we always assume that the signal is going down in frequency. But we've always been conservative. We've always, in almost every search, not all, but almost all of them, we have gone a little bit positive in our search over the frequency derivative. So typically it's been at the level of 10%. So you might go from negative 10 to the minus 8 hertz per second to 0 is your nominal spin down range. But then just to be on the safe side, we've typically gone another 10 to the minus 9 hertz per second positive. So in principle, we could have seen something like this already. But if you wanted to do better in your sensitivity, what you would do is customize your search to really focus in on that narrow range and spin down. And by doing that, you can basically refocus your computational resources, which allows you to lengthen the coherence time that you use in your initial stage of the search, and that improves your sensitivity. So there is some potential gain from focusing on a very limited part of the parameter space. The solar system objects, which involve different scenarios, but basically involve binary systems. You could have a couple of what are called compact dark objects just in our own sun, just hovering around the center of mass of the sun, and they're going around each other, and they're emitting radiation in principle. And you would expect it to have a very weak intrinsic amplitude because these are very light objects compared to ordinary stars, but they're a whole lot closer to us than the signals we normally go after. Instead of looking for something a kiloparsec away, you're looking at something that's 10 to the minus 5 parsecs away. It's a whole different scale of distance, and that gives you hope that you might be able to see it. And there have been searches carried out for that. Other possibilities to look for asymmetric primordial black hole emission, and searches have been carried out for that also. Those are, in some respects, a little bit like this boson cloud search, in that there you're actually looking at a merger process, but way, way, way before the merger takes place. So you have, again, a very tiny increase in your frequency with time. It's just the beginnings of a chirp. And so the overlap between that kind of a continuous wave approach and the approach used in the merger searches, where you have matched filters and template banks of chirps, there's a little bit of overlap in there. And that's also a very active area of research, is trying to, in some sense, bridge that gap between continuous wave methods and these so-called CBC methods. And then this final category, the ultralight dark matter detection, that involves some kind of, say, a dark photon field. There are other fields that could do this, that would interact directly with your interferometer mirrors and push and pull them. It's like a dark electric field has a very weak coupling to matter. It might be proportional to the baryon number, or perhaps to the neutron minus proton barrier number. And in that process, you would have a characteristic frequency given by the mass of that particle. You basically would say that h times frequency equals the mass of that particle. So it's actually a very monochromatic source right there. It has a very well-defined frequency. You do have to worry about Doppler effects, but they're actually less severe than they are for the case of continuous wave emission from a neutron star, because the Doppler effects come in at second order. We have a Maxwell velocity distribution that's just based on the fact that this ultralight dark matter is in the vicinity of our own galaxy. And so it has a characteristic velocity of about 10 to the minus 3 of the speed of light. But that gets squared when you look at the correction to the frequency and the correction to the mass. So you actually get signals that are narrower than an ordinary continuous wave signal, because the Doppler modulations are smaller. And in fact, what you can try to do is exploit that by tuning the coherence time of your Fourier transforms to match the number of cycles. And what you basically want is about 1 million cycles. And the reason you don't want to go much beyond that is that this is inherently a stochastic process. These ultralight dark matter particles, if they exist, are basically just fluctuating as a gigantic gas with enormous abundance number. Just, we're bathed in it in this model, and you just are looking for stochastic fluctuations in that background. And so it just doesn't last for much longer than about 1 million cycles before you start losing coherence. So you don't have the advantage you have with coherent signals, where you can just look longer and longer in your coherence time and get better and better signal-noise ratio. That doesn't work in this model. Okay, so I'm out of time. Let me just close with a few comments. So our conventional wisdom as to ordinary continuous wave sources is that our most promising sources would be young stars with a high-ish spin frequency, not high compared to millisecond pulsars, but high compared to the rest of the young pulsar population. Those could be known pulsars, or they could be unknown stars that may or may not pulsate. Another possibility is a millisecond pulsar with a relatively high spin down, or a millisecond pulsar with an already known upper limit on its ellipticity that's at the level of 10 to the minus 9 and might actually be accessible. I talked a good bit today about Scorpius X1. That would be a very promising signal, especially if an electromagnetic astronomer could detect pulsations for us and tell us what that spin frequency is. That would make the problem so much easier to solve. And then, of course, there's always the possibility of some outlier in the population that's not typical at all, but is there, and it happens to be relatively close to us, and we detect it gravitationally. So because of all of that, there's a great deal of uncertainty on what the best search strategy is in going after continuous wave sources. But I'll just note that nature has been remarkably kind to us before with 1509-14 and 1708-17, and we may get lucky again. All we need is one continuous wave detection of one neutron star in our own galaxy, and we have what I consider to be the ultimate multi-messenger astronomy source, because it's something that we can track for decades, generations, both electromagnetically and gravitationally, and really try to drill down and understand that system. And I think it would actually be quite a change in our whole outlook on gravitational wave astronomy. With that, I'll end and ask if you have any questions. Oh, thank you. Questions? If we have time for questions, I guess we have our photo. Any questions?
Okay, so we have some more time in the afternoon for a small discussion session. If you
Okay, great.
Okay. So let's thank Keith for this set of lectures. We are coming to the end of this course, and he took great pains to prepare his lectures as well as to come all the way across the world. So thank you very much, Keith, for doing this.